In this video, I'm going to discuss electricity output from a solar panel. And so this is for PHY 1020 on November 8th, 2016. We are going to discuss how much energy a solar panel produces, and obviously this will be dependent on the amount of sunlight that the panel receives. It should also depend on the size of the panel, the efficiency of the panel, the amount of time that we are using to gather that energy. And so I'm going to go through some sample calculations here. First thing, the sunlight that any panel receives obviously will depend on the geographical location. So this map of the United States, which I showed in class the other day, is showing the amount of solar energy that's received depending on the location. As you can see, the Southwest receives the greatest amount, whereas in Florida we are receiving less than that, and other regions of the country receive even less. Clearly the night and day variation should account for that. There are also weather conditions and the seasons will change. But generally speaking, the values are expressed in watts per square meter. That's an amount of power per area. And the numbers that are shown here are averages that take into account all these variations, night and day, seasons, and so on. So typical values would be on the order of a couple hundred watts per square meter. So for instance, in Atlanta, it's 182. Then it increases as you go south to 200 watts per square meter for us. It goes a little higher in Miami at 219 watts per square meter. For comparison, Los Angeles is at 225, pretty high by comparison. Phoenix, Arizona is at 224 watts per square meter. So as far as the size of the panel is concerned, obviously the bigger surface area, the more energy the panel will be receiving. It also depends on the orientation of the panel, the tilt of the panel, but we're not going to discuss that here. It's not a major problem for us at this stage. And so here's an example calculation. So as I said earlier, in Gainesville we are getting 200 watts per square meter. Let's consider a 6-foot by 6-foot panel, and we ask the question, how much power does the panel receive on average? So taking into account the average values that we have here, 200 watts per square meter. So the power received is going to be whatever power we get per area multiplied by the area of the panel. Okay, so for the panel we have 6 foot. We need to convert that into meters. The number I'm going to use here is 1.83 meters. So the surface area of the panel will be 6 by 6, or 1.83 by 1.83, which works out to 3.35 square meter. The amount of power received then is going to be 200 watts per square meter multiplied by 3.35 square meters, which works out to 669.78 watts. Very often we'll need the power expressed in kilowatts, and so to do so we will need to divide the number we just got by 1,000 to convert that back into kilowatts, and we end up with 0.66978, which we can easily round up to about 0.67 kilowatt. So that's how much power this panel will receive. That's how much energy it receives per second. We'll make the adjustment for time later. Another important parameter is the efficiency of the solar panel. So efficiency, we discussed that previously in class. That is the ratio of energy output versus energy input, or power output versus power input. You can use either or of those two definitions. The ratio is the same number. You cannot just mix energy and power. It both have to be either energy or both power. So for our solar panel here, what we need to measure is how much electrical energy is produced or generated by the panel versus how much solar energy it received in the first place. Or if we express those things in power, measure the amount of electrical power output versus the solar power input. Okay. And typical values for solar panels are somewhere around 10 to 20%. The world record seems to have reached now 24%, according to this recent newspaper, or actually website article, so I'll let you look it up later. So most panels are on the low end, and of course the price goes up with it. So a 24%, I didn't check the price of these panels, but they would probably be a lot more expensive than the 10% panels. So for this solar panel, the 6 foot by 6 foot, we already worked out that it's receiving 0.67 kilowatt. We are going, for the purpose of this calculation, assume that we have a world-class panel with a 24% efficiency, which will effectively mean 0.24 for the ratio. So 0.24 is going to be the ratio of the electrical power output over the solar power input, or as I said, the output over 0.67 kilowatts, since we've already figured this out. And now the electrical power output is going to be 0.24 times 0.67, which, if my math is right, should be 0.16 kilowatt. That's how much power is effectively coming out of the solar panel once we take into account its efficiency. Next, we need to also consider how much time is involved here, because what power companies charge for, or is charging for, is how many kilowatt hours you use. And as we discussed before, power is a ratio of energy over time, how much energy you consume or how much energy you produce, depending on whether we are counting power output or power consumption. So for our purpose here, the energy is equal to power multiplied by the time. Since we want the energy in kilowatt hours, we need to express the power in kilowatts. We've already done that. So now we need to figure out the time in hours. And typically we measure energy consumption in a month. So for specific calculations, we'll assume that it's 30 days. And the question then becomes, how much energy is generated in a month by our 24% efficient 6 foot by 6 foot panel in Gainesville? So here are some numbers we need to put together. So we already said it's producing 0.16 kilowatts with the efficiency involved. So we need to figure out how much time is in a month. 30 days, 24 hours per day. It works out to 720 hours in a month. So altogether, in a month, this panel will generate an amount of energy that would be 0.16 kilowatt. I'm sorry, an amount of power. No, I meant energy. Sorry. 0.16 kilowatt times 720 hours. That works out to 115.2 kilowatt hour. So this is the conclusion of this calculation, that the panel in a month would produce 115.2 kilowatt hours. There are a couple of things that I neglected in this calculation. One is, I've already mentioned the tilt of the solar panel. Another one is the conversion from DC to AC. So solar panels produce energy or electricity in the form of DC electricity, but what we use mostly in houses comes in the form of AC power. Everything that you use in an outlet is AC electricity. And so we need to switch that DC electricity into AC electricity. That's the job of a device called an inverter. And I'll show you what it looks like in a different video, but for the moment, just think of it as a box that takes in DC power and produces AC power as an output. So clearly then there becomes an issue of efficiency. How efficient is this process? Do we convert every kilowatt hour of DC electrical energy into a kilowatt hour of AC electricity? And the answer is almost. Most inverters are pretty efficient these days, and typical values are excessive of 80%. We are now closing in on 99% efficiency for some of those things. So it's something that we don't really need to worry too much about then, because it looks like we don't lose too much energy in the process of DC to AC conversion. And this is an article that I just found that talks about a 99% efficient solar panel. So if we try to put everything all into one formula, if you wanted to see that in just one big step, then the energy produced by the solar panel is the product of how much energy or solar power the panel receives, divided by 1,000 to convert that into kilowatts, multiplied by the area, then multiplied by the efficiency, and multiplied by the time. You could obviously multiply them in any order you want. As long as you multiply those four terms together, then you should be fine. What's assumed about the units is that the solar power received by the panel is going to be in watts per square meter. That's usually the unit that's provided. And And if it's the case, then we need to convert that into kilowatts per square meter. So remember, that's the factor 1,000 in here. We need to know the surface area of the panel. That should be in square meters as well. Now, for the efficiency, there is no units. It's a ratio. But we will need to use it in decimal value. So if it says 24%, then we would use 0.24 for the ratio. And then the amount of time that we use this for is in hours, and the final result then is going to be kilowatt hours. The outcome of this whole calculation is going to be kilowatt hours. A couple of things again, just to remind you that there are some details that have been neglected in this quick calculation. One is the orientation of the panel. Typically, panels are put on the south-facing roof, or at least the south-facing side of the roof. And then there's also a tilt that is above horizontal, how much of an angle the panel makes. There's some calculations that are involved there, but I'm neglecting that for this exercise, assuming that the panel is essentially flat on the ground. And then, as I said, the DC to AC conversion, but that's getting close to 100%, so it's something that should be, we can ignore. It's not a major factor.